We saw in the last section how we can use the rules for the indefinite integral to solve a definite integral and get a value that is exact rather than estimating like when we use Simpson's rule and trapezoidal rule. Now we're going to use some applications to solve a lot of different types of problems using a definite integral to get exact values. And the first we'll look at is the area between curves because it's a good visual. So let's look at a couple of functions. This is f of x. This is g of x. And if I want to get the area between the two curves, let's say from A to B, let's first imagine what it would be like to estimate that. And there's more detail about this in the lesson. If I look at a rectangle, the height of this whole rectangle is all the way up to function value at f. If I want the area between curves, I need to subtract off the little piece of the rectangle that's down here under G. So what I'll have is the whole entire rectangle minus the amount that's under G to give me the area between the curves. So I can write that as the area from A to B using the integral from A to B, which remember means let's sum up rectangles, of the function f of x minus g of x dx. So the f of x function has to be the one on top. So we can also write that, if you think of it as the integral from A to B of the upper function minus the lower function. Dx. So this is the way that we will solve our problems, and this will give us an exact value. Let's look at an example. So we want to find the area of the region bounded by y equals x cubed plus 6, y equals x squared, x equals -1, and x equals 2. Because we have to do upper function minus lower function, we need to know which function's on top. So you have to think about a data table or a graph or both. So if I just look at data, if I plug in x equal to -1 and x equal to 2, in my first function I'll call that y1. If I plug in -1, -1 cubed is -1 plus 6 is 5. If I plug in 2, 2 cubed is 8, and 6 is 14. For the function y2, if I plug in -1, I square it, I get 1. If I plug in 2, I square it, I get 4. This y1 function is on top, and this one's on the bottom. So if I graph it, that's what I should see. And so my integral goes from -1 to 2. The top function is x cubed plus 6. I subtract off the bottom function, which is x squared. And dx gives me my variable x and my width of my interval. And then I can find the value here. So taking the antiderivative, I would have x to the 4th over 4, antiderivative of x to the 3rd, plus 6x, the constant rule, minus x cubed over 3, and everything goes from -1 to 2. Plug in the 2 first. 2 to the 4th is 16 over 4, plus 2 sixes are 12, minus 8/3, minus, I'll plug in -1, I've got 1/4, plus or minus 6, minus a -1 over 3 gives me plus 1/3. You put all your fractions together and add everything up, you end up with 18.75. It's an ending decimal, That is the exact value of the area between those two curves. Let's look at a second example now that involves an exponential function. But again, the rule is the same. We need to know which is the upper function, which is the lower function on the interval from -1 to 3. So, looking at x at -1 and 3, if I plug in -1 here, I have 3 plus e to the -1. Well, e to the -1 is 1 over e. So this would be 3 plus 1 over e, which is just a little bit bigger than 3 for my 1. And if I plug in 3, I have 3 plus e to the third. E to the third is definitely bigger because 2.7 is almost 3 to the third power is very large. Our second function, 2x, negative 2x, excuse me, if I plug -1 in here, I get 2, which is less than 3 plus something. If I plug 3 in, I get -6, which is a negative number, has to be smaller than that. So in this case, again, the first function listed is the top function, and that makes that the bottom function. So to find this integral, it goes from -1 to 3. The first function, 3 plus e to the x, minus the second function, -2x, the one on the bottom, gives me -1 to 3 of 3 plus e to the x plus 2x dx. And we have to find the antiderivative first using those rules. So the antiderivative of a constant 3 would be 3x plus e to the x is the same thing, plus 2 times antiderivative of x, x squared over 2, and that now goes from 1 to 3. If I put in the 3 first, 3 3s are 9, plus e to the third, plus my x squared is 9, minus, if I plug in -1, 3 times -1 is -3, plus e to the -1, and then -1 squared is plus 1. So the exact value here, 9 and 9 is 18, plus 3 gives me 21, 22, plus e to the third, minus e to the -1, and this is the exact value. I can write my e to the -1 is 1 over e, like I did up here, but since the definite integral gives the exact value, we don't really want to put this in a decimal at this time. If this were a problem involving money, a different type of application we'll see later, then we would go to a decimal. But for now, this is the exact value, and this is where we stop. Okay, when I subtracted here, I should have subtracted that 1. So instead of 22, I have 18, and 3 is 21 minus 1. It should be 20 plus e to the third minus e to the -1. This next example we have to look at is under the title of area between curves by points of intersection. We can't do on an interval yet because we don't know the interval. All we know are these two functions, and since it said the region bounded by, that means they must meet. So we need to find where they intersect, set up a data table, and possibly in this case we'll look at a graph. To find the intersection, we set the two curves equal to each other. Four minus x squared equals -3x. Now we're working with a quadratic function and a linear function. I like my quadratics to have a positive leading coefficient, so I'm going to move everything over to the right side of the equation. That will give me plus x squared, still have minus 3x, and then subtract 4. And then to find the intersection, I have to factor. If it's quadratic, be sure you have a 0 on one side. X, 4, and 1. It's a funny 4. This needs to be minus, so it's minus 4 and plus 1. So when you set these equal to solve, x plus 1 equals 0, we have x equal to negative 1, and then x equal to 4. And so those are the x values where the curves meet. But to set up my integral, I need to know which one's on top, which one's on the bottom. Two ways to do that. You can do a data table or you could do a graph. If we look at the data, if x is equal to 1, my function y1 has the value 4 minus 1, which is 3. When I have x equal to 4, 4 4s are 16, 4 minus 16 is negative 12. For y2, if I plug in negative 1, I get my 3, and I plug in 4, and I get negative 12. Well, that's what's supposed to happen. But how do we know what's on top and bottom? We pick a point in the middle. So I've checked negative 1 and 4. Now I need to pick a point in between, and a nice point in the middle would be 0. So for the first one, if x is 0, y is 4. For the second one, if x is 0, y is 0. And so that does indicate that when I look here, that's the top curve. And then down here would be the second curve is the bottom curve. If you graph, you can see the same thing. Try to remember things you've learned before. You know, you can never forget anything from a math class. If this is a quadratic, it's a parabola. Coefficient's negative, it opens down. At 0, it goes through 4. So it goes up and down. Negative 3x is a line. Negative slope means it goes down. And if I'm interested in getting over to 4, when I do my intersection at negative 1, I have a line that goes down like this. So this is my y1 curve, this is my y2 curve, and my intersection goes between here at negative 1 and all the way over to here, little off scale here, at x equal to 4. And I want all the area inside here. So my integral goes from negative 1 to 4. My first curve, 4 minus x squared, minus my second curve. And then I get to do my subtraction. Let me this out a little bit here. Integral from negative 1 to 4 of 4 minus x squared plus 3x dx. Antiderivative 4x minus x to the third over 3 plus 3 times x squared over 2. And this goes from negative 1 to 4. If you put the 4 in first, back way over here. 16 minus 4 cubed over 3 plus 3 times 4 squared is 16 over 2. That's the first part, minus. Plug in the negative 1, I get negative 4. Minus negative 1 makes that plus 1/3. And then plus 3 times 1 over 2. Putting all this together, if you got a common denominator to get the exact value here would equal 125 over 6 if you were able to do common denominators. Don't have to do that. If you don't want to, you can always estimate. So this approximate value with the calculator should be 20.833, and the 3's continue. So you might want to check that to see even if you don't get this, if you can get that decimal. For this example, again, we just have to find the region between x cubed and 9x. We don't have an interval yet to determine what our integral limits will be. So to find the intersection, we have to set the two curves equal to each other. So we have x cubed equal to 9x. Do not divide by x. You cannot solve these by dividing by a variable. If you do divide by a variable, you will have x squared equals 9, x is plus and minus 3. I'll show you why that's a problem. Like with the quadratic, bring everything over to one side, set it equal to 0, and factor. So if I pull out an x, I'll have x squared minus 9 equals 0. And you could factor again, or you could remember that I'll let x equal 0. If x squared minus 9 is 0, x squared is 9, so x could be plus or minus 3. We have 3 points of intersection. This curve is going to intersect 3 different times. So we have to think about it in terms of our two curves, y1, y2. At 0, not 0, I want to go in order, -3 and 0 and 3, I should get exactly the same numbers for y1 and y2, because they meet. What I need to know to determine the curve on top and on the bottom is what happens in between. So just as a test, if I look at 0, if I plug in a 0 for x cubed, I get 0. If I plug in a 0 for 9x, I get 0. Plug in -3 cubed is -27. 9 times -3, -27. These are going to be exactly the same in those little bars. So let's check another point. Let's check at -1 and at +1. If I plug in -1 and cube it, I get -1. If I put 9 times -1, I get -9. For 1 cubed is 1. For 9x, 9 times 1 is 9. Okay, there's a problem here. Between -1 and 9, this one is on top. Right there. But between 1 and 9, this one's on top. So we have different functions upper on different parts of our curve. So I have to set up 2 integrals. One integral that goes between -3 and 0, because between -3 and 0, y1 is the top curve, so it's the first curve. And you subtract 9x. And since we're summing up, in your brain think rectangles, summing up rectangles, I have to add what happens on the second half, from 0 to 3. Well, from 0 to 3, the y2 curve is on top. 9 is bigger than 1, so it's going to be 9x minus x cubed. If you sketch a graph of it, you'll have y equals x cubed, and you'll have a straight line going between, it's kind of straight, between -3, 0, and +3, so this curve is on top, the cubed one. The line is on top here, so I have to have 2 separate integrals. So, do the integration. The first one, I've got x to the 4th over 4 minus 9x squared over 2 from -3 to 0. Over here, I have 9x squared over 2 minus x to the 4th over 4 from 0 to 3. When you plug in 0 over here, you get 0 over 4 minus 0 minus, and then you plug in your -3. So if you have negative 3 to the 4th over 4 minus 9 times, and negative 3 squared is 9 over 2. And then you get to the second piece here. Always put in this 0 because that's going to change the signs of what's inside the second piece here when you subtract. Be careful about that. I'll put the 3 in here. 9 times 3 squared is 9, gives me 81 halves minus 0. Oops, excuse me, I forgot to plug in the 3 here. 3 to the 4th over 4, 3 to the 4th power over 4, and then minus the 0 for the second half. Put all this together, probably with your calculator. You end up with 40.5. So be very careful and use parentheses and square brackets. The details are in here, and it's very important that you get those correct because these are exact values. Now we're going to look at total change in applications. You've seen this before. As a reminder, in general, the integral from A to B of a rate of change of anything, say profit, dq, which means q is the variable, is equal to the total change in the profit. For example, for profit, remember profit is revenue minus cost. So what you could have is the integral from A to B of revenue prime of q minus cost prime of q dq, because it would be the derivative of profit, which is revenue minus cost, which means the derivatives of revenue minus cost derivative. That would give us the total change in profit. Not the profit, but the change in profit. You start with an amount, you end with an amount, and the change is the difference, and that's what the antiderivative of the derivative would give us. So let's look at an example now, not of profit, but of something else. Our example dealt with imports and exports. Our formula for the rate of change of imports, I, equals 3.0 plus 6.2t. Now this is a rate of change with respect to time, so we could also write this as di, oh dear, dt. Not very legible there. Di dt. And exports, E, is the rate of change of exports over time. So that would be dE dt. Our T year starts counting in 1988, and the problem wants to know the difference between imports and exports between 1989 and 1998. So if we think about the integral, if it starts in 1989, our time period would be 1, and 1998 would be 10. So we want the integral from 1 to 10. So we need to know which of these curves is on top, say starting at 1 and going to 10. So let's test it. If I plug in 1, I have 3 plus 6.2 would be 9.2. If I plug in 1 here, this is just about 5. 4.1 plus 0.94. So imports are larger when T is 1, and if you plug in 10, you'll see the same thing. The values are larger for imports over this interval. So I comes in first. 3.0 plus 6.2t minus 4.1 plus 0.94t dt. But think now about what that means. Imports come into the country. We pay for those. We spend money. Exports are money that comes to us because we're bringing in, we're exporting goods that other people are paying for. Since imports are bigger, that indicates what we're going to have here is a trade deficit. Okay? Our imports are bigger than our exports. So let's see how much that is over this time period. Integral from 1 to 10, 3.0 minus 4.1 is a negative 1.1. Plus 6.2t minus 0.94t. And what a lot of people do is just leave them up there. If you put them together, it's 5.26t. We'll check that out. And then we integrate. Some people also like to put the t's first. Doesn't matter how you do that. So if I do the antiderivative here, I'll have a negative 1.1t plus 5.26t squared over 2. And this goes between 1 and 10. Equals, you plug in your numbers. Negative 1.1 times 10 goes in first, plus 5.26 times 10 squared is 100 over 2. And then we have to subtract off what we get when we plug in 1. Now remember, this is not a 0. We're plugging in a 1 here. So that would give me negative 1.1 plus 5.26 over 2. And when you put all that together, you should end up with about 250.47. Now this would be $1 billion of a trade deficit. This is just one of the examples in the lessons. Be sure to look at the other ones. Word problems can be difficult, and they will help you figure out exactly how to combine them to answer the question that you need to know. Consumer surplus is an economic term that you'll see in your other business courses. So let's see mathematically what it means. We have a demand function here. Remember, demand functions decrease because as the price equation, P equals D of Q, as price increases, demand decreases, or as the demand, the quantity demanded increases, the price decreases. At some point, this is called the equilibrium point, which we also have studied before. At that point, we have price, supply and demand equal. The market is in equilibrium. That's what it's called. Neither a surplus nor a shortage. If we just look at the demand equation compared to this equilibrium price, excuse me, the area between these two curves, the demand curve and the price line, give us consumer surplus. That's the amount that consumers will save because some people are willing to buy at a higher price, but the price the market is running at is down here. So that's the surplus, the savings to consumers. So to find the area between these two curves, the area is consumer surplus. It's the integral from 0 out to Q bar of the demand function D of Q minus the equilibrium price, and Q is our variable. So this is a formula that gives us consumer surplus, but it is an area between curves, which is why we're studying it in this unit. Let's look at an example now. In our example, we're looking at a quantity of cameras. The demand equation, negative 0.2 Q squared plus 80. The supply equation, 0.1 Q squared plus Q plus 40. In order to find consumer surplus, we need the quantity Q at equilibrium and the price P at equilibrium. So to find that, we have to set the two curves equal. We need to know when supply is equal to demand. 0.1 Q squared plus Q plus 40 equals. I like my Q squared is positive, so I'm pulling it over here. So I'll have 0.3 Q squared plus Q, subtract 80 makes it negative 40 equal to 0. We always want to try to get the 0 on one side and everything else on the other. This does not really seem to lend itself to factoring. It's not too bad, though, if you multiply by 10. You can use the quadratic formula. You could graph these two curves and see where they meet, and that would be the point of intersection, as long as you happened to choose the point where they intersected when you set up your data. So let's see about multiplying by 10. Would make that 3q squared plus 10q minus 400. And I can actually factor this one. 3q here, q. 400's got to be 40 and 10. Okay, 10 there and 40 here. 40, 30 gives me a 10, so I want my 40 to be positive. So this is how this factors. If I set the first piece equal to 0, I get q equal to negative 40 over 3. This piece gives me q equal to 10, and clearly a quantity cannot be negative. So the integral that we have to work with will have to have q equal to 10. So we're interested in the point where q is equal to 10. That's my q bar. And now I need to figure out what p bar is equal to. To do that, I can use either of these two equations and plug in q. I think if we plug in 10, maybe to this first one, it would be easier. 10 squared would be 100. 2/10 of 100 is 20. Negative 20 plus 80 is 60. So my price is 60. So my consumer surplus would be the integral from 0 to 10 of my demand equation. It's always d of q minus p bar dq. So negative 0.2q squared plus 80, and then minus p bar, which is 60, dq. Integral from 0 to 10. Just go on and find the antiderivative there. Negative 0.2, and this uses the power rule, q to the third over 3. Plus 80 minus 60 is plus 20. So that will be 20q, and this goes from 0 to 10. Get all that together, multiply it all out, combine your terms. When you plug in 10 and then you subtract off, you do have a 0 here, and it'll just give you 0. And you should end up with 133.3333, and so on. What tells us is the savings to consumers, which is what consumer surplus is. So the savings is to consumers $133.33. We just saw previously to this consumer surplus. Now we're going to look at producer surplus, and the graph looks very similar, but it's not, because this is the supply curve. Supply curve increases. As prices increase, more quantity is supplied. As more quantity is supplied, that's because the prices have increased. So the supply curve is an increasing curve. Here we have our equilibrium point, where producers and consumers are both happy because producers will supply exactly what consumers will buy. This area down here is the producer's gain. Producers, some are willing to supply more at higher prices, but all these producers who are supplying at a lower price are gaining because the equilibrium price is above it. So the area here gives us our producer surplus. The area from 0 to q bar, that's the interval on that axis, and the curve on top this time is the price curve. Y equals p prime. It's a constant. Subtract off the curve under here is the supply equation. Now, suppose we have a supply equation. Let's say we have an equilibrium point where the quantity is 6 and our price is 13. The supply equation that goes with that is 2q plus 1. When you subtract, you get 12 minus 2q, or whatever yours turns out to be. because you have to subtract both pieces. And you simplify that, and this should turn out to equal, I think, $36, something like that. It's an example in the lesson. Also, be sure to do these examples in the lessons that go with this. They have exactly the kind of thing that you need to carry through beyond this course. You've seen the formulas for consumer surplus, the integral from 0 to q bar of the demand function minus p bar, the equilibrium price, and producer surplus, which was the equilibrium price minus the supply equation. So you evaluate those integrals and you come up with consumer savings or the gain to producers. If you combine those two, you have social gain. It's the gain for both consumers and producers put together. So you can add these together and you get the integral that gives you the area between these two curves, the supply curve and the demand curve. Well, if you look at these equations, if you just add consumer surplus and producer surplus formulas, you get social gain, integral from 0 to q bar. You can do sums and differences with integrals. Here's p bar minus s of q plus d of q minus p bar. Okay, the p's subtract. You've got demand equation minus supply equation. That's your social gain formula, gives the area between the two curves. If you've already found producers and consumers, you can just add the numbers together, which is not likely in this course, or you can just use this formula from the beginning to find the social gain.